I'm going to do a famous example of limits, although it's not always phrased that way, but it should be. And that is, what is 0.9 repeating equal to? That when you have a decimal representation, repeating decimal, specifically 0.9 repeating, 9's forever, what is that equal to? And you may or may not have seen the answer. This is a great example. That the key here, absolute key, is that you need the notion of limits to actually define, to actually implement the careful standard definition of what a repeating decimal means. And this is an interesting thing. We are taught a little bit about repeating decimals pretty early on, usually in elementary school, because decimals are super useful practical things, and you want to be able to do things like 1/3 equals and say, what's the decimal? And that just doesn't have a terminating decimal. It has to be a repeater. And then you just sort of assume that you know what that is and how to manipulate it and what it means. And nobody who sees this first in elementary school knows what it means. Nobody, because it's actually a limit concept, the careful definition. And so it's really a basic calculus concept that we're accidentally introducing in elementary school. It causes real confusion, especially about this one. Another thing that's confusing here, just to get this out of the way, is that there's an implicit assumption that's often made by students, which is that every real number has exactly one decimal expansion. In particular, the decimal expansions are unique. And that's just not true unless you disallow things ending in series sequences of 9s. It's just if you allow things like this, and you totally can, and I'll show you what happens if you allow it, then you get multiple ways of expressing certain real numbers. And they don't tell you that in elementary school either. They probably feel it's unnecessarily confusing, and honestly most elementary school teachers don't know that fact. Okay, so if this might be part of your intuition, if you're confused by this, you might be implicitly assuming, but wait, how can two different visually appearing expansions represent the same thing? They can. It's not part of the uniqueness is not really part of the system. Okay, so we really need a limit. So what does this notation actually mean? Okay, well, a finite decimal expansion is a sum of coefficients, single digits, times powers of 10, in this particular case, negative powers of 10. And this is 9 times 10 to the minus 1, plus 9 times 10 to the minus 2, plus 9 times 10 to the minus 3, plus dot, dot, dot. Okay, we still got the dot, dot, dots, which means we're not done writing down the careful definition. Okay, so what we really have is extremely similar to Sn that we had before, so we're going to just use Sn again. Okay, this is a finite sum, and this is again a geometric summation. And we're going to take that out to 10 to the minus n. Okay, so that's just the finite decimal, 0.999 dot, 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 9, and where there's n decimals. And by definition, this is a perfectly defined rational number. It's just 999, 9,999,000, that kind of thing, over 10 million, that kind of thing. And we define the infinite, the meaning, the real number defined by this infinite decimal symbology to be the limit of that sequence. So let's just write that down. By definition, this is equal to, I'll put a little colon, computer science terminology, sometimes math terminology for this, is defined to be the limit as n goes to infinity of that S sub n sequence. Or it's the limit of, you can use summation, you'll need a dummy variable there, 9 times 10 to the minus n. And actually, yeah, that's fine. And that's, of course, often symbolized as an infinite sum, but again, the key is that that's dangerous. That hides the limit definition. Ooh, that's a k, sorry. N tells us where to stop. The k is a dummy variable that tells us, while we're writing down the summation, it's 9 times 10 to the minus 1, and then 9 times 10 to the minus 2, all the way up to n. Okay. If you don't like summations and dummy variables, it's just the limit as n goes to infinity of 9 times 10 to the minus 1 plus all the way, and then stop at 10 to the minus n. Okay. So this is a geometric summation. The same trick applies as before. For that finite sum, there is a perfectly nice shortcut to do that summation. Nothing to do with calculus or limits or anything like that. And that's just going to be equal to, okay, it's just that first, it's just that 9 times, well, let's see. So the ratio, the negative exponents can be a little weird, so I'm going to rewrite it one more time. 9 times 1/10 to the n. Okay. So, various different slight variations on how you do the shortcut formula, but often you say, let's look at the first term. That's a sub 1, let's say. It's the first term in the summation. Times, and then you take 1 minus, now the ratio is 1/10. The common ratio is 1/10. So you take 1 minus 1/10. You look at how many powers you needed to multiply that ratio times the original term. Well, that's n minus 1, just because it happened to be we started out with 9/10 and not 9. And then you add 1. Well, that actually boosts it back up to n. And then over 1 minus 1/10. Okay, so I'm doing this a little quickly because there's plenty of places to look for the shortcut formula for the sum of a geometric sequence. Okay, in any case, the fact that this is equal to this has nothing to do with anything weird whatsoever, just clever algebra with finite sums and powers, things like that. Okay, so we can simplify that. Okay, we get a lot of cancellations here. We get 9/10 from that first term thing, and we actually get 9/10 on the bottom as well. Boom, they cancel. 1 minus 1/10 to the n. Okay, so it's a limit very, very much like what we had before. Instead of 2 to the n, it's just 10 to the n. Okay. And then again, there's a couple of strategies of how you would prove that that limit, carefully that that limit is, well, the claim is that this limit is 1. And again, since this is about like epsilons and n's, let's do it the somewhat hard way. We're going to say let epsilon be greater than 0. Okay. And then, very much like what we were just doing, let n, let's take the log base 10 of epsilon. Okay. That's going to be some really big negative number, because epsilon you want to think of as super small usually, and so it's a negative power of 10. So take the negative of that, and then take the ceiling for safety. Okay. Then, okay, because we chose this in a clever way, if little n is anywhere after that stopping time, n, we're going to have that 10 to the n. The ceiling made sure that we went just a little bit further if we need to. It's going to be greater than or equal to 1, let's see. It's going to be greater than or equal to 1 over epsilon. So we're taking 10 to a negative power, makes it 1 over, and then cancels with the log 10. Okay. Or in other words, 1 over 10 to the n is less than or equal to epsilon. Let's see. Oh, this was greater than, so I can make this a greater than. So if I allowed little n to be exactly n, I might just be right on the nose. And that's not a big deal, but it's nice to follow the strict definition that you want to be actually, you want this to be less than epsilon. But that's okay, because little n is bigger than n. Okay. And so 1 minus 1 over 10 to the n is bigger than 1 minus epsilon, and it's certainly less than 1 plus epsilon. It's clearly less than 1. Okay, and there we go. There's the terms of our sequence, cleverly written, not as a summation, and that was a big deal, but again, it had nothing to do with limits. And it is in our error bounds. So if you want the picture, again, the picture is our proposed target is 1 here. I'll sort of exaggerate a little bit how different 0.9 is from 1. There's our first one. 0.99 is right there. That's that. 0.999. And of course, it actually gets close much faster because powers of 10 get small really quick. And there's our sequence getting very close. And what did we do? We said, take somebody who only really cares out to like the 6th decimal place. Are they going to be satisfied? Absolutely. Just let big N be equal to, guess what? 6. If you have 6 nines, by definition, pretty much, that's close enough to 1 if somebody only cares about the 6th decimal place. Or maybe the 5th, I guess. If you want to say, like the rocket scientist, the super careful engineer, rocket engineer, whatever, who needs to do everything to super decimal places to get the space probe off to Pluto at exactly the right time and place, they want to have 12 decimal place accuracy. Okay, how many 9s do you need? Well, yeah, maybe give it 13. If you just write out that finite approximation and you get lazy, you're like, I don't want to keep writing 9s. I know that in principle I have permission to keep writing 9s as long as I live, but to this accuracy, if I write 13 9s to 12 decimal place accuracy, that's 1. Okay. And if I want to get 17 decimal place accuracy, I just write a few more 9s. And if I want to get 27 million decimal place accuracy, I just write about 27 million 9s. And it's really important what's going on here, and this is one reason I wanted to do this example. I'm not saying that any particular one of these finite decimal expansions is equal to 1. That's not true. But by saying that the infinite repeating decimal is equal to 1, it's going back to like that first video. What does that mean? It means that if I analyze this process of 0.9, 0.99, 0.999, 0.99999, and I look at the trend to which it's going, that's going to be 1. Or to be more precise, anybody who takes this symbol, which is an idealization, really, because you're never actually going to write down the infinite number of 9s. You're never going to use an infinite precision calculation, let's say. But it says no matter who looks at this, and no matter what kind of accuracy they want, they can choose a finite number of 9s so that it will be within their accuracy. So it's really it's important that there's a real subtlety to all these limit concepts, that you've usually got some sort of practical calculation or a family of practical calculations like finite decimal expansions. And you could say something really complicated about it. Say, okay, 0.9 is this kind of number, and 0.99 is this kind of number, 0.999 is this kind of number, and just have a whole book full of like, what are all those finite decimal expansions like? It's a really nice, it is a really nice shorthand to say maybe the limit of a finite sequence of 9s is just 1. And it's, of course, an even more nice shorthand to say the repeating decimal is equal to 1. And there is a problem with going from here to here, as I said at the start of this video. This hides a limit concept, and most people have never seen that. Most people think they know what the definition of this is, and they don't. Not the standard definition. The standard definition is as a limit. And that's true even of like 0.3 repeating. That's the definition by definition. That's the limit of a bunch of finite 3s. If you do the calculation, it is exactly 1/3. They weren't lying in elementary school when they said that 1/3 has a repeating decimal representation. They just were sort of implicitly lying by not actually telling you what the definition of that symbol is, which is not how mathematicians, not how mathematics is supposed to work. Okay, that's plenty on this particular example.